we're very used to using rectangular coordinates to describe the position of a point in the plane, but there are actually a lot of choices that you have to make to come up with that rectangular coordinate system. Let's see exactly what goes into describing the position of a point. So if we're trying to describe the position of, say, this point in the plane, first we have to choose an origin, which I'll call O, and then you have to choose a coordinate axis, which usually we start with the positive x-axis, and then you extend that axis to get the negative x-axis, and the perpendicular direction becomes the positive y-axis, and usually we make the positive y-axis counterclockwise from the positive x-axis, and that also determines a negative y-axis. Then to determine the coordinates of this point, we sort of decide on what length counts as a unit length, and then we see how many units over that point is, and that becomes the x-coordinate of the point. So this point would have x-coordinate 3. And then we take that same yardstick, or that same unit length, and measure how far up that point is, or down. And that tells us the y-coordinate of the point. So this point would also have y-coordinate 3. So the coordinates of this particular point in this coordinate system with all of these choices that we've made is 3, 3. And since this is using a rectangular coordinate system, let me put a little r right here just so we remember that this was using the rectangular coordinate system. Well, we made a lot of choices there when we decided how to describe the position of this point. So here's another version of this same point. Let's see if there are any other natural ways we could decide how to describe the position of this point. So just like before, we'll decide on some origin and some axis. But rather than measuring distances over and up, there's another natural way to describe the position of this point in the upper right. Let's call this A. Another natural way to describe the position of A is to just say how far it is from the origin. Let's call that number r. And then to describe the angle that you would make with your axis down here. And let's call that number theta, because it's an angle. So this point A would be r, theta. And this way of describing the position of a point in the plane is called polar coordinates. And so when I'm using polar coordinates, I'll put a little subscript p on my coordinates, just so we remember that these are polar coordinates and not rectangular coordinates. Okay, so polar coordinates, just like rectangular coordinates, there are 2 numbers that you need to describe the position of a point in the plane. But rather than both coordinates being distances, only one coordinate is a distance, r, and the other is an angle, and that's theta. R typically comes first, and theta comes second. This axis here is called the polar axis. And I've written it, I've drawn it going to the right. It doesn't have to go to the right, of course. And we'll usually imagine that there's some yardstick along the polar axis that defines the distance units for r. Okay, so with this in mind, let's try plotting some points in the polar coordinate system. So let's plot these points. So let's start with this one. Why don't we call this A? So 2, pi over 3. So to plot this point, let's have an origin and a polar axis with some distance markings on it. So even though the r coordinate comes first, I find it a little easier to think about plotting points in polar coordinates by thinking about theta first. So what I do is I take the polar axis and I rotate it to this angle. So that's going to be like this. So there I've made the angle pi over 3 from the polar axis. And then along this direction, I count out as many units as I have for r. So for this one, that's 2 units, which is going to be something like this, 1, 2. And so this point right here is 2, pi over 3 in polar coordinates. Okay, now let's try B. Okay, so again, when you're plotting points in polar coordinates, you need an origin and a polar axis. And let's make some distance markings on our axis. So this time the angle is negative 3 pi over 4. So we need to start out by making the angle negative 3 pi over 4, which is going to be about like this. So there's our angle. And now our r value is negative 3. So it's a little bit funny to have a negative here because we said r was a distance. Distances can't usually be negative. So if we want to allow our coordinates to be negative, we have to decide what that means. Well, if positive r values go along the direction that the angle points, it kind of makes sense that negative r values should go in the direction opposite from what the angle points. So in this particular angle, negative 3 pi over 4 points down into the left, and so positive r values would send you down into the left for this value of theta, but negative r values will send us up and to the right. So since our r value for this point is negative, we're going to go up and to the right. Let's copy down some distance markings, something like this. And this r value is negative 3, so we're going to go in the negative direction, 1, 2, 3. It puts us right there, up in the first quadrant. So notice that even though this theta value was put us in the third quadrant, this point is in the first quadrant, and that's sort of a combination of where theta points and what r is. So one thing that makes polar coordinates kind of tricky is the theta value doesn't totally determine what quadrant you're in, so you have to be a little bit careful. All right, let's look at this last example. C, so negative 2, negative 2 pi over 3. Let me put it down here. So again, we need an origin and a polar axis. All right, so first we need to draw this angle, negative 2 pi over 3. So that's going to be something like this. All right, I didn't make any distance markings. Let's make some distance markings, something like this. And so positive r values would send us along this angle, but the r value for this point is negative, so we're going to end up going in the negative direction, so the direction opposite the angle points, and we're going to go 2 in that direction since the r value for this point is negative 2. So that's going to be right here. All right, so this is the point negative 2, negative 2 pi over 3, and that's in polar coordinates. All right, well, if you look at all of these examples, there's actually something funny that's happened. The point for A and the point for example C, these are actually the same point. If you measured the angle that this negative axis makes with the polar axis, that's pi over 3. And so another name for this point right here would be, if you use the angle pi over 3, right, that would make up and to the right the positive r direction, and you'd go 2 units in that direction. So another name for this point in example C is 2, pi over 3 in polar coordinates. So that really justifies that the 2 points from example A and example C are actually the same point. And this is kind of another unfortunate thing about polar coordinates. We're used to rectangular coordinates where every point has a pair of coordinates and each pair of coordinates gives you a different point. Polar coordinates doesn't work the same way. It's true that every point in the plane has polar coordinates that describe it, but every point actually has more than one possible pair of polar coordinates that describe it. And in fact, it's worth keeping track of just what all of the possible pairs of polar coordinates are. So let's look at an example. Let's find all of the possible polar coordinates for this point, 1 comma pi over 4. I guess maybe we should start out by really understanding where this point is. So if this is our polar axis, to graph this point, we'd draw the angle pi over 4, which is going to be like this. And we're going to go in the positive direction, so along the angle instead of in the opposite direction. And we're going to go a distance 1. And so this is the point that we're talking about. Okay, so one possible pair of polar coordinates for this point is 1 comma pi over 4. That's the pair of coordinates we started with. But let's find other pairs of coordinates. Well, since any coterminal angle also points in the same direction, we could just go around again and use the same r value, and that would put us in the same spot. So we would still be going an r value of 1, but we would add 2 pi to this angle, to the theta value for this point. And probably we should actually add those up. So 2 pi is 8 pi over 4 plus another pi over 4. That's 9 pi over 4. But, we could add not just 2 pi, but 4 pi. We could go around twice instead of just once. So 4 pi is 16 pi over 4 plus one more is 17 pi over 4. You can see that we could add or even subtract any multiple of 2 pi. So to be perfectly general, we could use the polar coordinates 1 comma and then pi over 4 plus 2 pi times any integer. And as usual, I'll use a k to mean any integer. So actually, there are infinitely many pairs of polar coordinates that describe this exact same location in the coordinate plane. But actually, we haven't even found them all, because what if the positive theta direction went down and to the left? Then the negative direction would be going up and to the right, and we could use a negative r value to get to this point. So what angle would this be? Let's see, this would be, well, that would be our pi over 4, but then plus a half turn. So that would be pi over 4 plus pi. And then instead of going 1 unit in the positive direction, we'd go 1 unit in the negative direction. And so the r value would be -1 for this pair of polar coordinates. And then we could do the arithmetic for the angle. So -1 comma 5 pi over 4 in polar coordinates. But, just like with all of the positive r value points, we could add any multiple of a full turn and we'd still have a valid pair of polar coordinates for this point. So we could have -1 comma 5 pi over 4 plus any multiple of 2 pi. So plus 2 pi k. So these 1 comma pi over 4 plus 2 pi k and -1 comma 5 pi over 4 plus 2 pi k, those are all of the polar coordinates for this single point. For this reason, often you'll see people restrict the theta values that are allowed when they use polar coordinates. Often you'll see people restrict themselves only to angles from 0 to pi over 2, and then only use positive r values, or maybe angles from 0 to pi, and then use positive or negative r values. So you kind of have to pay attention to whatever convention is being used by the source that you're looking at. There's actually one point in the plane where all of this doesn't work. There's a single point that works differently, and it's the origin. To be at the origin, well, whatever theta is, r has to be 0. As soon as r is non-zero, you're stepping away from the origin. So if you want to be at the origin, r has to be 0. But if you aren't stepping away from the origin, it doesn't really matter what direction the positive r direction is, and so theta can be anything. So the origin is actually 0, any angle. So you can see for every point in the plane, it has lots of different pairs of polar coordinates.